Okay, this is calculations over the calorimetry cup, the lab that y'all did to determine the specific heat of an unknown metal. I'm going to start with a general drawing of a calorimeter cup where you have the outside container. The inside container you chose between 50 to 100 milliliters of water. This group chose 75 milliliters of water, which translates to 75 grams. Because the density of water is 1 gram per milliliter. The specific heat of water is 4.184 joules per gram degree Celsius. That is a constant. These numbers you would obtain from your graph. Your TIW is 25.1 degrees Celsius for this group's data, and the T final was 27.2 degrees Celsius. My change in temperature for the water is TF minus TIW, which is 27.2 minus 25.1, or overall 22.1 degrees Celsius. Okay, now we heated up an unknown metal in boiling water for 10 minutes in a dry test tube. You weighed your metal before you put it in there. This group had 5.76 grams. The specific heat of the metal was unknown. We took the temperature of the boiling water for this group. They registered a 101.7 degrees Celsius. So my delta T is going to be TF minus TIM, which stands for temperature initial metal. So my TF is coming from, at the end, your stat on your graph, you got 27.2 for this group, minus 101.7 degrees Celsius. I should get a negative because it was warm and it's going to be cooled off by the water. The water is going to gain the energy from the metal. And so I get a negative 74.5 degrees Celsius for my delta Tm. Okay, so if we set this up, then we have our hot side, which is our metal, is equal to our cold side, which is our water. But if you recall from your lab, that was not the only thing that was actually in the calorimeter cup. You also had a stirring rod, okay? And that stirring rod also had its own mass. So let me go up here and... So the stirring rod is 29.97, and its specific heat is set for you at 0.385 joules grams degrees Celsius. But then you also have the container itself, and that container also has a mass. And so for this group, the mass of their cup was 56.2, and the C for the cup is 0.91, and that will be the same for everybody. Now with that in mind, what we're going to do is we're going to put all those variables in. And so my equation now has my metal with a negative sign out in front of it equal to MC delta T of the water plus MC delta T of the cup plus MC delta T of the stirring rod. And since the cup and the stirring rod and the water are all in the same system together, all interacting with each other, they're going to have the same delta T. So I'm going to go back to my data and I'm going to plug my numbers in. Again, these will all be given to you with the exception of the specific heat, which is 4.184, which you were expected to know. Here's the specific heat of the aluminum cup, and here it is of the stirring rod. Then I will simply do my math on those, sum them. Notice here I keep the negative on the inside of the parentheses, then I have the negative on the outside of the parentheses. My next step, I'm going to get rid of this negative. A negative becomes a positive. It's still attached to the CM. So then I must do the multiplicative inverse and divide. My units are correct because CMs are joules per gram degree Celsius. And I'll get an answer of 1.84. Now, most metals have a specific heat less than 1. This one happened to be aluminum, and so aluminum standard is 0.91. And so the last step of our data is we're going to do our percent error. And remember, that is the accepted minus the experimental, which is what you derived. That is an absolute value bars, divided by 0.91, which is the accepted value again, times 100. For this group, they had 102% error. This can be explained by the low mass quantity that they used. Maybe they didn't heat it as well as they should have. Maybe they didn't transfer as fast as they should have. There's errors that you should be able to count for since you've done the lab as well.